Here is a great real-world application of differential equations. We can use differential equations to model exponential growth and decay. I want you to think about the following fact. The bigger a population is, the faster it can grow. That should make sense. The more people there are, the more people they can make. The more disease there is, the more disease it can make. The more, let's just look at cells. Cells split into two using cell mitosis. And if you have one cell, it will split into two cells using that process. And each of those two cells will split into two of their own daughter cells. And then each of these four are going to split into two each for a total of 8. And every time the mitosis happens, we're going to double the number of cells. And this is exponential growth. That's exactly what exponential growth is all about. A consistent multiplying factor over a period of time. So we're going to go ahead and say that this happens every 5 hours. We're going to say that the first cell exists at t equals 0, and then 5 hours later, it has completed cell mitosis, and we now have 2 cells. 5 hours after that, our population doubles from 2 to 4. 5 hours after that, our population doubles from 4 to 8. And 5 hours after that, our population doubles from 8 to 16. From a calculus perspective, we can see that the rate of change of the population is also exponential, right? We can look at this rate of change from t equals 0 to t equals 5. Our population changed by 1, and our time changed by 5. And then from t equals 5 to t equals 10, our population went up by 2, and our time went up by 5. And then over this next interval, our population went up by 4, and our time went up by 5. So the key concept here is that we're finding that that rate, dp dt, the rate of change of the population with respect to time, is directly proportional to the population. So whatever the population is, we're going to multiply that population by some constant to get the rate of change. Notice that we multiply 1 by 1/5 to get this. We can multiply 2 by that same 1/5 to get here. We can multiply 4 times 1/5 to get that dp dt, and we can multiply 8 by 1/5 to get this dp dt. So this concept, hugely important concept, of the rate of change being directly proportional to the population, that is an inherent property of exponential growth, population growth. Okay? And it ties into the fact that the more there is of something, the more they can make of themselves. Okay? So what this turns into in an equation is that the rate of change is directly proportional to the original value. When something is directly proportional to itself, when something is directly proportional to something else, it means that there's some constant k that you can multiply a scalar factor by so that you can get from one to the other. So we can turn that very important statement into this equation right here. And what we'll do is we'll solve this differential equation by separation of variables. The variables are p and t. They are not k. K is a constant. So I'm going to multiply both sides by dt to get the t on the right side, and then I better move that p over to the left side. So the separation part of this is going to be dp over p is equal to k times dt. So we have separated the variables. Now we're going to integrate, which is great. And when we integrate this equation, we're going to get that the natural log of p is equal to k times t, because we're integrating with respect to t, plus some constant of integration. I'm going to ignore the absolute values. Turns out they don't really matter, so we don't really need them in this case. All right, so I'm going to solve for p. That's what it asks us to do. So we're going to exponentiate. We exponentiate this. We take e raised to the natural log of p. That's going to give us p. And we're going to get e raised to the kt plus c. And I believe we saw this earlier. A very, very common trick here is to say, well, instead of writing this with a sum in the exponent. Let's turn this into a product, right? Because if we multiply like bases, we can add the exponents. So we're going that property in reverse. And remember that E is a constant, about 2.7, and C is that constant of integration. So a constant raised to a constant is some new constant. So I have some constant times e to the kt. Okay, this is the result of a population being directly proportional to its rate of change. Okay, so this is something that we will want to memorize, but it's really not so hard to go through that process of separating and integrating and a little bit of log and exponent property to get to that equation right there. This is a very important equation that we'll use a lot in exponential growth. All right, so I'm going to try to model this scenario with that generic answer that we just got, the general solution. To do that, I'm going to use the first two known pairs, 0, 1 and 5, 2. You don't have to use those two, but they're the smallest numbers. Why not keep things easier? So 0, 1 and 5, 2 are the two different initial values that we're going to use in order to find the particular solution. So it's always best to start with the easiest one. P of 0 is equal to C times e to the k times 0. And k times 0 is 0, and e raised to the 0 is 1. So P of 0 equals C. And I'm given that P of 0 equals 1. So C equals 1. So that means that we have P of t equals 1 times e to the kt. We still don't know what k is. K is some other constant that we need to find. Now, it looks like k is equal to 1/5, but I was actually approximating dp dt up here, so it's not going to equal exactly 1/5. But it should be very close to 1/5. Let's see what it is exactly equal to. P of 5 is equal to 1 times e to the k times 5, or e raised to the 5k, which we're told is equal to 2. So this is an equation that we can solve for k. We want to solve for the exponent. We're going to take the natural log of both sides. Natural log of e to the 5k is 5k. Natural log of 2 is just a number. And then we can divide both sides by 5 and get natural log of 2 over 5. All right, so that means that P of t is equal to 1 times e raised to the k, which is, I'll write it as 1/5 natural log of 2, times t. Now that is the particular solution to the equation of population growth for this particular population of cells. One thing we could do if we choose to, not required, but is kind of a nice thing sometimes, we can get a little fancy with our properties of logs and say, well, I know that I've got a 1/5 and a t outside of the natural log. So I can multiply them together. T times 1/5 is t over 5. And then I've got the natural log of 2. I don't really love that I have an e and a natural log in the same equation, so I'm wondering if I can cancel them out. And I can, but not yet, because what I have to do first is get this coefficient of t over 5 into the logarithm. Okay, and we can do that. We know how that works, right? We can bring that t over 5 as an exponent of the 2. That's a property of logs that we've seen before. Oops. And that step right there leads us to say, oh, e raised to the natural log of stuff is just equal to the stuff. So 2 raised to the t/5 is our population. And that we might have been able to figure out even without any calculus. So it's nice to see that the calculus works, but it also is nice to see that our intuition also works. Just try plugging in t equals 0, t equals 5, t equals 10, t equals 15, all the values that show up in our table up above, and you'll see that we're going to get populations of 1, 2, 4, 8, etc. So this is a nice connection between exponential growth that you've probably already seen and differential equations, which is, of course, what we're studying right now.